Warning: this experiment uses toxic and carcinogenic reagents and directly handles extremely hot liquids. Gloves, protective clothing, and a fume hood should be used. This should be performed by or under the direct supervision of an experienced chemist. Greetings, fellow nerds. In this video, we're going to make cadmium selenide quantum dots, a type of nanoparticle with interesting properties. First, we need to make our source of selenium. Get 30 milligrams of pure selenium powder and add to it a stir bar. Then add in 5 milliliters of 1-octadecene and turn on the stirring. Now add 0.4 milliliters of trioctylphosphine. Keep stirring and gently heat it until all the selenium dissolves into a clear liquid. What's happening is the trioctylphosphine is reacting with the selenium to form trioctylphosphine selenide. Once it's ready, seal it and let it cool. This will provide us with about 5 experiments worth. Now get 13 milligrams of cadmium oxide in a flask and place in a glass thermometer. Mine happens to be a glass encapsulated digital thermometer. Now add to it 0.6 milliliters of oleic acid and 10 milliliters of 1-octadecene. Now heat the mixture until the cadmium oxide completely dissolves. What's happening is the cadmium oxide is reacting with the oleic acid to form cadmium oleate. After the cadmium oxide dissolves, keep heating until the mixture hits 225 Celsius. While you wait, get everything set up. Have a dozen or so small vials or test tubes and prepare a syringe with 1 milliliter of the trioctylphosphine selenide solution from before. Be ready, because you need to work quickly. Once the cadmium solution reaches 225 Celsius, inject the selenium solution and give it a quick shake. Now immediately start withdrawing small samples of the solution, about half a milliliter to a full milliliter, and put them into the vials. For the first several samples, try to do this one after another as fast as possible. Then withdraw only when you see the color significantly change. What's happening is the cadmium oleate is reacting with the trioctylphosphine selenide to form cadmium selenide. These particles start small but grow in size the longer the solution reacts. Now this growth only continues if the temperature is maintained, so withdrawing it at regular intervals and placing it in a room temperature vial stops the reaction and locks the particles into their current size. So by controlling how long they stay in hot solution, we can control their size. The oleic acid surrounds or caps the particles and keeps them from aggregating. Okay, now we've made quantum dots. These particular quantum dots are fluorescent in the visible region, and if exposed to an ultraviolet light will fluoresce different colors. Now scientifically, we have to ask the question, if all the samples have exactly the same chemical composition, why do they have different colors? The difference arises because the particles are so small that the allowed quantum states of the electrons in them are partially determined by the particles' shape and size, not just on their composition like in bulk materials. The best analogy I can think of actually is a stereo system. Large speakers are really good at producing long wavelength low frequency bass sounds, while smaller speakers are really good at short wavelength higher frequency sounds. This is due to differences in the size of the diaphragm and the frequencies it can support. Likewise for quantum dots, the smaller the dot, the smaller and bluer the natural wavelength of light it will emit. The bigger the dot, the longer and redder the light it will emit. Quantum dots are being researched because there are many applications such as making solar cells more efficient, better display technologies, and even medical imaging applications. So even if you can't make them in the lab, I'm very sure you'll soon encounter them in your daily life. Thanks for watching. Please subscribe, like, and comment. The procedure in this video was based on this article published in the Journal of Chemical Education. Now an additional experimental note if you try this is that you probably won't actually see this broad range of color with your eyes, since the wavelength differences are actually very subtle. You'll probably only see yellow and green. That's all I'm actually seeing here in real life, but a good high-definition camera will automatically color compensate to give the appearance of this broad range you're seeing in the video. So to observe these differences, if you don't have a fluorescence spectrometer, look at the samples through a good digital camera.